Hi, myself Harshav, and I'm going to brief you of what our project is about. Discuss challenges that we face building the project and how we can develop the project in the future. My teammates Ankit and Devanshi are going to show you the code and live demo of functioning of a project and its features. The motivation behind the project is to deliver a highly interactive AR object for better visualization of complex scan data by layman, which usually requires a medical expert to understand. So, who are our target audience? This project can be useful for doctors to diagnose a disease. Doctors can further visually show the patients and explain them about the disease. Medical students can use this project to interactively learn anatomy.
Good afternoon, sir. Myself, Yanshiva, along with Ankit Kumar Patel and Ashwin Saravanan, would like to present our J component topic 3D viewing of MRI and CT scans and images in AR. By looking into the topic, one can understand that the project is divided into two subtasks. Firstly, 3D viewing of MRI CT scans in AR, and secondly, images in AR as 3D meshes. I am here to explain you the first objective of our topic. We have used here BTK library, also known as visualization toolkit. This is used to create a mesh out of the data fed into it. Here I have some DICOM images. Like there are three DICOM images as the slices of front and back of it, and an entire head DICOM images. Uh, as we know that MRI datasets are used for medical model training and testing, especially for working on segmentation process. We go through the process of first building the point data cloud of the brain scans, which after that we try to get the mesh out of it. For that, here you can see that every MRI and CT scans are represented with Hounsfield value, which is actually the intensity or the depth given to each point of the scans. By changing the threshold value, we can actually view the brain's gray matter or the bones or the white matter respectively. What we have set is here as per the user's requirement of that threshold. We'll set all the value below it as 1 and all the values are above it as 0, so user can view the required piece. After that, we actually get the point cloud data of the mesh of that 3D data with the required threshold value, and we update it. As we know that in visualization toolkit, it has mappers, actors, renderers, and window as a part for visualizing it. So here, where we in this section of the code, we are actually setting those actors and mappers and renderers. These actors are actually the object which we are trying to view as a 3D mesh. Here we can change the property as the background and the color and opacity as per the user requirement. And at last we are storing those data as in STL file. As we This VTK supports STL file conversion very easily. So we are going through that. After running this, here we can see this is the renderer window which is popping up. This is one of the data set which shows the top view of the MRI. Here I have set the Hounsfield value as 100, so it is showing the entire portion and the other noising fields over it. But it's a 3D mesh with the thing, that's why it is rotating and all. But if we change the Hounsfield value as 100 and 1500 and rerun it, we can see that the noisy values and other white matter of that brain cells are removed, and only the required portions and the pipelines are actually viewed. This is the It also shows that whatever, since the DICOM, this dataset has just 10 to 12 slices of this front value, top view. That's why it is as a thin. You can see the 3D mesh as a thin sheet, but there is another data if which shows the entire head of it. Here you can see this is the MRI, the mesh of the MRI, which is having the entire human head, and you can see we have set the opacity to 0.2, so we can view the internal brain sections of it also, as well as the outward. And this is the zoomed view where we can see that actually the triangular mesh is implemented over it. Thank you.
Good afternoon. Myself Ankit Kumar Patel. I am here to explain you the second objective of our project. For accomplishing the desired results, the procedure follows with three steps. Firstly, to get depth maps from the input images. In 3D computer graphics and computer vision, a depth map is an image or image channel that contains information relating to the distance of the surfaces of seen objects from a viewpoint. Hugging Face Transformers is a platform that provides the community with APIs to access and use state-of-the-art pre-trained models available from the Hugging Face Hub. We are using GLPN model from Hugging Face Transformers for receiving the molecular depth estimation with vertical cut. This is the architecture used for the transformer model. Next, it is necessary that the image has background for predicting depth. The transformer model predicts or estimates the depth using the pixel intensities of the image. So now I will show you the code. This block has all necessary packages imported for accomplishing this step. Next, we have taken a simple sofa image from the internet and uploaded in our drive to use it. We resize the image for better point of viewing and model can predict the depth. This is the input image after resizing. And this line of code next is helps to extract the necessary points of data from an image, or in short, it does a feature extraction step. Next, the line the this the predicted depth is received, and we can see it after plotting here. This ends our step 1. Next, we have our second step. Now we move down. Here we try to get point cloud data from depth maps. A point cloud is set of data points in space. The points may represent a 3D shape or object. Each point's position has in set of Cartesian coordinates x, y, z. This point cloud conversion from depth maps is possible by a library named as Open3D. Open3D is an open source library that supports rapid development of software that deals with 3D data. The Open3D frontend exposes a set of carefully selected data structures and algorithms in both C++ and Python. Normalizing the depth map to get point cloud is achieved in the shown lines of the code. Thus, we finish with 2D, that is our second step, and approach to the last step, creating a mesh. In 3D computer graphics and solid modeling, a mesh is a collection of vertices, edges, and faces that defines the shape of polyhedral object. The faces usually consist of triangles, that is triangle mesh, quadrilateral square mesh, or other simplex polygons, n-gons. Since this simplifies rendering, but may also be more general composed of concave polygons or even polygons with holes, we calculate the normals and set center of the mesh first and then get out as mesh object, which will be saved as a OBJ file. Open3D provides mesh to be stored as OBJ file, which cannot be directly rendered in AR. For so here you can see that we have tried it to save it in .fbx file, and it's showing false. So Open3D does not allow it to save in FBX form. So we need to save it in OBJ form, and to for AR we need to convert it like the OBJ to FBX file using the Blender. Now we will visualize our objects in AR. First, I will show you in MeshLab. So this is the sofa object. We are visualizing our sofa using MeshLab because it will show the proper texture. And if we if we are visualizing it in AR, the texture is not shown there. So as you can see, this is our sofa. Next, I will show you the MRI image here also. That is in MeshLab. This is the MRI CT scanned image. It has a opacity of 1. This is the from down you can see. Here is the inside the skull, there is brain and all. Now next I will show you in AR using Unity. So first I will show you the sofa. This is Microsoft 3D Viewer. We are using it to view. So now this is the in AR. Next I will show you the MRI in AR. So this is the AR of the MRI that can be visualized. Thank you.
So what are the advantages of our project? Through better visualization of the data and faster identification and diagnosis of the disease is possible. This project can act like an extra arm for doctors. You can expect instant results as soon as you put the scan data. There's no waste in time or there's no latency. So there's faster diagnosis also. So what are the challenges that we faced while developing this project? Getting masked images of the dataset is difficult. Such public dataset was not available. Proper MRI dataset for our own application is not present as open source due to many laws and regarding patient's privacy. So we use dataset that are generally used for segmentation procedure and models. Integrating the mapper for 3D to AR is a challenge. Many issues were faced regarding conflicting file formats during our implementation from 3D to AR. The task to convert our mesh to FBX format is not automated. The file supported for developing AR requires FBX format, and models we have does not support to store mesh as FBX. We stored it as object and STL, which is exported as FBX via Blender. for accomplishing the task correctly. So we need to find a way to automate the task. So what is the future work that, so what are the future work that we can do? We can make an app where user can input MRI DICOM file for an MRI brain scan and get an AR model of MRI scan on your phone screen seamlessly. We can make better UI for enhancing user experience and develop faster and more efficient algorithm. We can extend the functionality by providing segmentation features, texture changing, and opacity adjustment, even for high user understanding.